Hello! We did the effects of Tylenol and dopamine on movement, C. elegans. So I'm going to explain the introduction. So basically what we did, we used acetylcholine because it causes muscle contractions. It's a neurotransmitter released in neurons, and like I said, it causes muscle contractions. So we did two different types of C. elegans worms. We did wild-type worms, which were N2, and we did mutant worms, the slow one. So the slow one mutant worms, they have a mutation which causes them to have an increased concentration of acetylcholine in the synapse. So the C. elegans, the N2 worms, they have a good amount of acetylcholine. It's perfect. They have homeostasis of that. So when you have a decrease of acetylcholine, you have muscle weakness, and when you have too much of it, you get paralysis because all your muscles are contracted. So acetylcholine is broken down by acetylcholine esterase in the synapse between neurons. So what Tylenol does, it's an acetylcholine esterase inhibitor. So if you inhibit the thing that breaks down acetylcholine, you will have an increase of acetylcholine in the synapse. And dopamine, it disrupts the balance of acetylcholine. It kind of balances it out like a little seesaw thing that we used to play when we were little.
In this experiment, at first we prepared our agar plates. We added some nutrients like sugar, salt, cholesterol, and then we added our E. coli. Those E. coli feed on nutrients and grow. And when they grew, we cultivated our worms by chunking, and when the worms grew, we added our medication. For preparing our medication, we use two kinds of medication, Tylenol and dopamine. For preparing Tylenol, we got Tylenol 500 milligram from the over-the-counter pharmacy, and then we crushed it and we solve it in S buffer, and for completely solving it, we just put them in the stir plate and let them solve in the S buffer, and then we filter it and diluted it to 20 millimolar concentration. And for dopamine, we got 0.5 gram dopamine powder, and we solve it in the S buffer, we filter it and dilute it to 30 millimolar solution, and then we add those medication to our worms in 3 different time frames: 1 hour, 2 hours, and 3 hours. And after that, we did trashing. For trashing, we got 100 microliter S buffer. We pour it on the plate contain worms, and then we suck it up immediately, and when put it in the small microfuge tube, and when we put it under the microscope, and we count the number of moving and the worm's mobility, and then we average them and compare the results.
I'm going to be talking about the results of the experiment on our N2s. When we administered the dopamine and introduced it to them at 3 hours, we saw a decrease in movement. As you can see here, there was a drastic decrease. At 2 hours and 1 hour, there's not much of a change. When we look at our slow ones, there was a decrease in our 3 hours. And then also the other two, there was an increase, but we're thinking that it could be due to the half-life of dopamine only lasting for about 2 minutes. So it's just a hypothesis, but we're not sure. When we're looking at Tylenol, we saw an increase in all of them, and the reason why we're hypothesizing that is that the acetylcholine esterase inhibitor causes the acetylcholine, all of the acetylcholine release is too much, so it's causing everything to slow down, and then the increase of movement. On the slow ones, we saw an increase at 3 hours. And so the other two did have a little bit of an increase in some of the trials, but mainly on the 3 hour. And then when we compared the means and standard deviations, we did see a big difference in the slow one, Tylenol. I can't see it too well in the picture, but we did see the drastic change on the 3 hour time frame for Tylenol. We had 4 that had a significant p-value, which was the 3-hour dopamine, the 3-hour Tylenol, and also the 2-hour Tylenol and 1-hour Tylenol.
Okay, in our conclusion, honestly what we expected to see with the N2s after administering dopamine was that their movements would decrease. After 1 hour we did see a slight decrease, but nothing substantial. After the 2 hours there was almost no change in movement at all in the N2 worms. However, after 3 hours we saw an unexpected rise in the movement. For the slow one, we expected to see a rise in movement due to the balancing out of acetylcholine and dopamine in the synapse. For hour one, there was a slight increase in movement, but not significant. At 2 hours, it did show an even greater increase than the 1 hour. And after 3 hours, the slow one movement finally decreased slightly, which made no sense because of the half-life of dopamine. It should have been out of their system by now.
Okay, so I'm going to be talking about the results of Tylenol. The Tylenol caused a higher concentration in acetylcholine, which should have caused a complete paralysis in the slow one worms. In hour one, there was no movement. In hour two, there was an increase in movement. In hour three, there was a more significant increase in movement, which led us to predict that, or hypothesize that the slow worms were making more dopamine, which makes sense because the Tylenol only has a half-life of 3 hours, which caused it to most likely wear off within the worms.
Thank you, Professor Twitchell, for your support and guidance through this research project.
As well as thanks to Professor Sophia Hines and Denise Brown for helping out in all the ways they did.
Thank
Thank
you.
you.